I'm Stephen Hicks, and we're in the Nuffield Department of Clinical Neurosciences at Oxford University. Right, so my research is in the field of visual prosthetics, and we're working to produce a computer-aided visual device to assist people who have just a small amount of remaining vision to get a better quality of life and increase their independence, mostly by their ability to see and recognise a few more things than their blindness or visual impairment allow. Our work is in vision and eye movement in the field of neurodegenerative diseases. In some respects, we look at eye movement difficulties with problems like Parkinson's and Huntington's disease. In other respects, we look at problems with the visual system itself, such as disturbances of sight related to cortical damage, such as stroke, or in the case particularly for here, we're looking at ways to augment vision in people who have visual impairments, such as macular degeneration or retinitis pigmentosa. Our technology works in several ways. We're using computer technology to understand the visual world for a person who has got visual impairment. So when visual impairment happens, you've lost the ability to get high-resolution images through the eye and into the brain, as we normally do in order to see people and environments, and importantly, read words. We can use a computer to do a lot of the visual processing for a person. And these days, computers have reached a stage where they're small enough and powerful enough to do a lot of real-time visual processing, such as person recognition or depth recognition, and in certain cases, they'll be able to read words. So we'd been working on this project for a couple of years to see if we can get computers to augment the sight for people who have got only a small amount of vision left. The simple idea is that a computer will recognise objects of interest and display them in a way which is simplified and bright enough for a person who has only a small amount of sight. We would be using a simple pair of glasses with small LED lights built into the lenses themselves. These are bright enough to be seen by someone with poor vision, and we can drive those directly by our computer software. This essentially gives a bright image where a person is, or a bright image where a nearby object is. And by that, the person can orient themselves in the environment, allow themselves a little bit more independence in getting from place to place, and restore some of their quality of life. One of our main aims for this project is to produce something which is discreet and unobtrusive as possible. And nobody really wants to wear a bulky camera or computer headset. So we've worked with the Department of Physics to produce a small, lightweight pair of glasses, essentially, that will look as normal as possible. They'll be transparent, but they have tiny cameras built into the frames themselves. The LEDs are actually minute and they fit into the lens. Now, we don't think this is going to be expensive technology at all. In fact, we're strong believers that assistive technology should be as cheap as possible. If you think about the cost of the components that are in this device, you have tiny cameras, which are very, very cheap in today's mobile phones. LEDs cost a cent each. Glasses frames don't cost very much either. The most expensive part is actually the computer that would run it. And essentially, we're using the same components that are inside smartphones. This is a small development board that runs at 1 gigahertz. So it's similar to a laptop from 5 years ago. It's cost about £120. The total cost of these devices will be very low, and it's very satisfying to think that we'd be able to produce this at a cost which is going to be available to people who will benefit most. So what we have here is a demonstration of some of the main components for our visual prosthetic as we've been developing them. The glasses on the polystyrene head there have a tiny camera centered right on the bridge of the nose. This is feeding visual data into the computer, which is doing the first pass of the processing. You can see here the cameras are absolutely tiny. They're actually completely discrete. So the camera image is going into the computer and it's simplifying it into a bright visual array. You can see here on the LEDs, this is representing the type of an output for 2 eyes. So they're duplicated left and right eye. You can see if you just get the camera image straight through, you can't really make too much sense of the bright blues of the environment thereby. But if we start doing a little bit of motion detection, and the simplest type is simply just a bright square on anything that moves, and it will pick up objects that are moving in the area nearby. This is bright enough to be seen by someone with blurred or low vision. If I put the two on top, as you move around the environment, you'll see the bright blue shifts, and the orange is tracking the region of the screen that has the greatest movement. And this is just a very simple process, which is running here on a laptop, but we can run quite simply on a little portable computer. One way we're thinking about exploring when all this is tied up and done is using eye tracking to integrate a little bit of gesture into the device itself. And a normal-sighted person, we imagine, may be able to use this just for fun, essentially, to do things like answer text messages or read a Facebook update. By having a small icon gleam in the corner of their view, if they look up to that, then you could synthesize that and play it into their ear.